Welcome. Thank you everyone for coming along. So my name is Brani Rusanov and I'll be presenting a presentation on ion chambers and reference dosimetry specifically for NV photons. And I'll be presenting with Andrew first. The first part of this presentation will cover a lot of theory to do with how we perform reference dosimetry as well as engineering principles behind ionization chambers. And then Andrew Hurst will go through his experience at Panzer and a lot of practical things that go into actually measuring absolute dose. So we want to ask the questions: what are we interested in? Why we want to do that, and how do we do that? So what do we want? We want to be able to accurately and precisely measure radiation dose from a linear accelerator. And why do we want to do that? Well, we want to be able to calibrate that linear accelerator, first of all, during commissioning when it first comes into the hospital, but also routinely throughout use, such that we can monitor its dose output and ensure that it behaves within tolerance. And that's important because it leads to a greater agreement between the planned dose that you calculate on your treatment planning system. So every patient has a unique plan, and given the nature of these treatments, it's very high doses next to critical organs at risk. So you want to make sure that the dose you're delivering is accurately represented in your treatment planning system, and then it's actually being delivered, and you're not delivering less or more than what you think you are. And that ensures better and more consistent patient outcomes, because there's a whole literature on the radiobiology and how the amount of dose you deliver to sensitive organs, how that leads to either tissue killing, tumor killing, or sparing of your organs. So you want to make sure that you're within tight tolerance of your LINAC output. Your LINAC is outputting within a tight tolerance. So how do we achieve this? Well, we need a device and a strategy to determine dose in water. And we use water as our medium of interest because the human body is more or less equivalent to water, and water is cheap. It's easy to work with. It's available everywhere. So that's we define our reference dosimetry in a water medium. So this requires a dosimeter of high accuracy and precision with known behavior and uncertainty for different conditions. So as you're going to see, performing any kind of dosimetry involves a lot of correction factors, conversion factors, and we need to accurately have a model of our dosimeter and of our medium in order to correct for the perturbations that dosimeter causes in our medium. And this also requires defining a set of standard conditions that we can replicate. So standard conditions that are defined at the primary standards laboratory, which are informed from international guidelines, so that all centers can kind of share the same information, have the same standard, and then that chain of information, or that chain of kind of setup conditions, is passed down to those primary laboratories, and they're passed down to end users like this hospital, so that we can basically replicate the same conditions and ensure we're measuring the same thing as what is measured at the primary laboratory. So what do we want? We want to be able to measure a quantity, and we need to define what that quantity is. So starting from basics, KERMA is is the way that we define the quantity that we want to measure. So KERMA stands for kinetic energy released per unit mass of the medium that you're measuring. And the concept of KERMA narrows down the type of energy transfer we're interested in. So we're interested in energy transfer from uncharged ionizing radiation, in this case, photons, megavoltage photons. And just a caveat, we're limiting this conversation to photons and not electrons, because you can treat with other modalities like protons and whatnot, but we're only talking about photons and how those photons deliver energy to charged particles in our medium of interest. And we're interested in KERMA because DNA damage due to charged particles is the main contributor to the biological effects associated with tumor ablation, and that's what we want. We want to basically destroy the tumor with high accuracy and precision. A more relevant quantity, though, which is derived from KERMA, is the absorbed dose. So this is a clinically relevant quantity, which is a measure of the kinetic energy transferred locally in a medium of interest. Again, from charged particles, and is measured in units of Gray, which is joules per kilogram. So there can be many positive, negative ions created from these interactions, but we can limit our, again, just to simplify our discussion, electrons are our particle of interest. An absorbed dose differs from KERMA in that some of the initial liberated charge that's given into the medium can be dissipated in the form of radiative losses. So when you have an electron that's created from an ionization event, that electron can either lose its energy through kinetic interactions or through radiative interactions, which means it creates a photon and loses its energy that way. But that photon is not going to contribute to damaging a local area. For example, in a tumor, it's going to deposit that energy elsewhere. So we need to not take into account those radiative losses, but only take into account the kinetic losses in our point of interest. And this is a nice little diagram that illustrates what I just said. So we have a high energy MV photon entering our medium, say water or a patient. It deposits energy in the form of KERMA, so kinetic energy released. It creates a whole lot of electrons, which then can either lose their energy through radiative losses or kinetic energy. And we're interested in this circle or sphere, which we define as where we want to measure our absorbed dose. And it's basically electrons crossing that region, depositing their energy, basically losing velocity, and in the process breaking, for example, DNA strands. We're interested in measuring that quantity. So KERMA is the sum of both the radiative and kinetic energy deposited by the electrons. Absorbed dose is the local kinetic energy losses only. And KERMA is proportional to the photon fluence. So the more photons you have entering, the greater the KERMA is going to be. And the absorbed dose is proportional to the electron fluence. So the more electrons you have, the more energy deposit, the more absorbed dose you're going to have in that region. And it's important to note that absorbed dose and KERMA do not occur in the same location. Since electrons deposit their energy along tracks, whereas photon interactions are more or less point-based. And yeah, generally, the equation, what we're trying to find out is the difference between the energy of the electron going into that region of interest and the energy of the electron going out of that region of interest. This is a useful diagram. Not sure if you've seen it before, but it shows you a plot of the collision KERMA, which is the energy that's transferred to electrons that then deposit the energy with kinetic in a kinetic manner rather than a radiative manner. And then this is the solid line is the absorbed dose in a region of interest. So you're going to notice that at depth 0, so say at this depth here in our absorbed dose region of interest, the KERMA is going to be maximum, as we have a maximum number of photons entering our medium, and so there's a maximum number of energy transferred to electrons. But our absorbed dose is a minimum because those liberated electrons haven't traveled any distance yet to deposit their energy. Then we reach what is called Z max or D max. So this is the depth at which you achieve the maximum dose. And it's the difference between Z0 and Z max is the build-up region. And this, you define Z max as the point at which you reach charged particle equilibrium. So what this means is that you reach a point at which the number of new electrons being produced is equal to the number of electrons, I guess, ending their, coming to an end of their track. And so that initially you have a lot of electrons being produced, and because they have a finite range, they're still depositing energy, but you come to a point at which they start to come to the end of their track, and at that point you no longer, or you reach that equilibrium point, and your absorbed dose is at the highest point. And then after that point of maximum dose deposition, the attenuation of photons as they travel deeper into the medium means that you have less photons, and so your absorbed dose is going to decrease by a proportional amount to the attenuation of photons. So you're going to have a proportional decrease in your KERMA and absorbed dose. So this chart helps inform us as to how we set up our measurement conditions when we're forming reference dosimetry. So keep in mind the build-up region, how steep this the dose gradient is, and then where our maximum dose point is. It's generally a flat region, and then there's this transient charge particle equilibrium where we have a steady decrease in our dose, but it's fairly linear, and the gradient isn't as high as it is in its build-up region. So shifting a bit towards what's called Bragg-Gray cavity theory. This was a theory I think developed in the 60s to try and relate quantities measured in a cavity, so in an air cavity, for example, an ionization chamber, and relating that quantity, relating the quantity of charge measured in that cavity to dose in that same spot as if the cavity wasn't there. So we're dealing with several different issues here. First, water and air are of different density, atomic composition. So there's going to be conversion factors and perturbations involved, which is why there's so many corrections involved. So just a simple definition. It's a Bragg-Gray cavity theory. Is a simple theoretical framework that relates the absorbed dose in water to the absorbed dose in a dosimeter, which would be air. So water to air, or air to water. And there are several conditions that need to be met in order for us to make this jump between dose to air and dose to water. So first of all, the electron fluence and energy spectrum should not be changed by the presence of that cavity. So what that means is when we insert the cavity, we want to minimize the change in how many electrons are going to be attenuated or produced, or their energy spectrum in the presence of that cavity. So practically what this means is the cavity has to be very small compared to the range of the electrons. And that's a good approximation to satisfy that condition. Second of all, the absorbed dose in the cavity is deposited solely by electrons crossing it. So we also have photons in the medium, but we're assuming that these photons don't interact with our cavity in any way. And it's not just the cavity, there's also electronics in the stem of the ionization chamber, which I don't know if you've seen it being passed around. But what this means practically is that all of the components should be as water equivalent as possible in terms of mass density and atomic composition, such that the rate of electron production is the same within the cavity or within our ionization chamber and within the medium. And the third condition is that measurements should be made under charge particle equilibrium or transient charge particle equilibrium. So what this means practically is that we should be taking our measurements in the linear portion of the depth depth graph, such that the ionization chamber is not positioned in the high gradient portion of the graph. And this is important because in that high gradient region, you have a big change in dose over a very short amount of depth. So because your ionization chamber has to have a sufficient sensitivity, it has to have a relatively large volume. So you're going to run into volume averaging effects where you're not going to be able to resolve the dose at a good enough level in that high gradient region. So yeah, you want to conduct your measurements after Dmax, ideally, or at Dmax. And also this more or less means that the number of electrons going into the chamber equals the number of electrons going out of the chamber. And it just generally helps with reducing your measurement uncertainty and beam perturbations. So once we satisfy all of those three conditions, this allows us to minimize the perturbance of the beam by the chamber. And once we can do that, once we've achieved that, then we can relate the dose to the medium and the dose to the cavity by simply taking the ratio of the electron mass stopping powers. So that's what that means, is that when the electrons is basically the ratio of the energy loss per unit distance of the electrons traveling through water and the electrons traveling through air, and that's this ratio here. So if we multiply the dose in the cavity by this ratio, we can approximate the dose to the medium as if the cavity wasn't there. This is a theory from the 60s. In practice today, Bragg cavity theory is used more as a guideline for the engineering of ionization chambers and for measurement setup. In practice, the use of Monte Carlo methods to estimate the dose is more accurate, and that's what's currently used for absolute dosimetry at primary standards laboratories. And that's performed from a graphite calorimeter using Monte Carlo methods. You can then estimate the dose given to water in what Andrew's going to cover in his presentation. But just to say that Bragg-Gray cavity theory isn't fundamental, but it's used to inform how we perform relative dosimetry. So a little bit about the design of the ionization chamber. So they're devices that measure the amount of ionizing radiation. So the devices that measure ionizing radiation by collecting the liberated charge within their sensitive cavity volume. So as photons cross that sensitive volume, they're going to ionize air particles, and we have 2 electrodes, one positive, one negative, and they're going to collect the ions produced from these ionization events. And then we relate those ionization events to dose, basically. We also need an electrometer and ion chamber combination, and this is used to measure the total charge within that sensitive volume. And we need the electrometer in order to provide a potential difference between our positive electrode, which is a thin coating on the outside of the ion chamber, and our central electrode. When you have a potential difference, that enables the ions created in that air region to be accelerated to either of those electrodes and therefore collected before they recombine. And there's 2 different kinds of ionization chambers used in the clinic. We have cylindrical and parallel plate. So cylindrical, this top image here, which you might have seen passed around, and then parallel plate looks like this, where it's kind of like sandwiched, where you have your electrodes basically, one on top here, and then one on the bottom. But how do ionization chambers work? So, like I said, we need to apply a voltage bias between the electrodes, and we do this to improve the efficiency, the collection efficiency of our ionization chamber. So you can apply a whole different array of voltages between the 2 electrodes, but what you will notice is that if you apply too little voltage, then ions will recombine before reaching the electrodes. So as you go from, say, 0 voltage to this first point, as you increase the voltage, you're going to increase your number of ions collected, and that's because you're reducing the amount of recombination occurring. If you apply too much voltage, say between V3 here and V5, then you're accelerating your ions too much, and they lead to subsequent ionizations, which actually create more ionizations not due to your primary radiation. That leads to an avalanche of new ions, and that again is going to increase your ion pairs collected. So what you want is a sweet spot region, kind of intermediate voltage around 250 volts, such that we minimize the number of ion. We minimize the loss of ions, but also we don't create any new ions.
Brani, I just wanted to say also with this graph, it's a good one to know for your studies. You might get the exam things coming up. This one's really important to know for how ionization chambers actually work and the difference between the dosimeter and survey meter. So it's a good graph to know. So make sure you understand that one.
Andrew is leaking examples.
I don't know, I haven't seen the exam, but if I made an exam, that's what I'd put on it.
But he's right, yes.
So this is a really good graph to know.
It's the example.
And if you don't understand it, definitely go look it up in a textbook and make sure you understand that one.
Absolutely, yeah, Andrew's spot on with that one. So as a quick example, a Geiger-Müller counter that doesn't measure the magnitude of your dose, but it's going to measure if there is a dose at all, and that's because it's very sensitive. You have a very high voltage, so the slightest ionization occurring in that sensitive volume is going to be detected, but it's not going to tell you how many ionizations are happening, just that something's happening. So, yeah, just hints over there. So what are some of the design principles with ionization chambers? So we have a thin central electrode made of a metal, for example, aluminium or graphite. So why it's thin is that you want to minimize the perturbation of the electrons that cross that sensitive volume, and the difference between, say, aluminium and graphite is that aluminium will have a greater sensitivity to ions, but it's going to be less water equivalent, so it's going to perturb the beam more. Whereas graphite is going to have a lower sensitivity to ions, but it's going to be more water equivalent. So there's benefits and negatives to using each one. Depends on the specific use case there. You have a thin outer electrode coating, again, aluminium or graphite, and for the same reason, depends what specific benefit you want out of your ionization chamber. Water equivalent encasing, so this is again used to minimize the perturbation of your ionization chamber and improve its energy response. And as you see, the energy response is quite common. It's quite a big factor in ionization chambers. So the way photons deposit their energy or contribute to collisional KERMA is highly dependent on the atomic number of the medium they're traveling in. So any deviation from, I think, water's 18, atomic number of effective atomic number about 18. So aluminium is going to be a bit higher than that. So you're going to have a greater number of electrons produced due to the photons. So you want all of your materials to be as water equivalent as possible. And that ensures that as the energy of your photon beam changes, the response stays the same between your ionization chamber and your medium. But if the materials are too different, there's going to be a differential response. So there's a lot of correction factors that go into addressing that. There's something else called a guard ring, which is quite significant for parallel plate chambers. So they're positioned here. They're basically a third electrode with the same bias as your outer electrode. And the purpose of the guard ring is to reduce leakage current due to ionizations in stem. So what that means is, say you have photons crossing the stem here or here, any electrons produced in that stem can leak into your sensor, into these collecting electrodes. So what that guard ring does is it collects them and basically removes them. So it's it improves the accuracy and reduces the uncertainty of your measurement. It also improves field uniformity. So the uniformity between your two electrodes is improved by having a guard ring in place. So that again ensures that the collection efficiency is as high as it can be. And it also reduces electron in-scattering effects. This one might be a little more difficult to understand, but basically, if we have water all around our ionization chamber, there'd be a uniform scatter produced in all directions. But because of the presence of the ionization chamber and it's filled with air, we have less scatter coming out than what's coming in. So you have this kind of the charge difference between what's in the volume versus what's outside of the volume is not at equilibrium. So you're going to have a greater number of electrons wanting to come into that medium. So by having the guard ring in place, especially for a parallel plate chamber, you reduce drastically that in-scattering effect. And that's a big reason why parallel plate chambers are used for electron reference dosimetry. Example. Electrode potential difference. So we apply the potential difference to reduce reduce losses due to ion recombination, and an atmospheric vent. So all of these ionization chambers, they're open to the atmosphere, so they're not sealed. And this is done in order to avoid potential pressure buildup within the volume, which may either damage the device or lead to a kind of a poor response of the ionization chamber. But if they're vented, we can measure the temperature and pressure in our room, and therefore apply basic corrections to correct for the temperature and pressure of our room. And as we assume that same air is filling our cavity, so it's easier to correct for those deviations. And now some operation principles. So this is when you're actually using these in the clinic. So So you want to position the chamber axis perpendicular to the beam if you're using a cylindrical chamber. So this diagram, if this is the beam, you want to make sure that your ionization chamber is perpendicular to the beam. The sensitive volume is perpendicular and not parallel, because then you're not irradiating the stem, and you're also reducing kind of the distance, the depth of your sensitive volume is shorter, which means you have a greater resolution in that direction. So that's useful for taking the sensitive depth dose measurements, for example. The effective measurement point. So this is a concept to do with the geometry of the chamber itself. It's basically when you take a measurement, there's a finite volume that you're measuring, but you're relating that volume to a single point that you're actually kind of defining that dose to. So for a cylindrical ionization chamber, that effective point of measurement is basically at the geometrical center of the chamber, whereas for a parallel plate chamber, it's at the entrance window on the inner side of the entrance window. And so you need to make, when you're setting up your device, you need to make sure that you're not positioning it at the geometrical center, but at the top side of the window. And there's quite complex equations that basically prove that that is where your dose that you're measuring is most likely or is most related to. Temperature and pressure correction, as I mentioned earlier, so this corrects for the number of air molecules or the mass of air in your volume. So if you have more air molecules in your volume, you're going to have different response of your chamber because there's more ions there to be created based on the pressure and temperature of air. Ion recombination correction. So this corrects for the loss of charge due to the recombination of positive and negative ions before they reach the electrode. So even with a bias, you're still going to get some loss in efficiency. Polarity correction. So this corrects for the differing response of the ionization chamber based on, say, if the outer electrode is positive and the inner one is negative. If you flip those polarities, you get slightly different response, and that's because it's a function of the energy of your beam, of the depth of your beam, of the field size that you're irradiating with. But basically, there's a different amount of positive and negative ions being created, and so to correct for this, you would measure with both polarities and take the average, and that's one way to correct for it. Also, the electrometer correction factor. So this is not explicitly corrected for, but when we basically assign an electrometer to every ionization chamber, and we don't interchange every electrometers with ionization chambers. And this is because every single electrometer has a slightly different response, slightly different characteristics, just because of the manufacturing process. And so you assign all of your correction factors to your ionization chamber and your electrometer pair, and you would never kind of not use them together. And then you have your calibration coefficient. This is an extremely important value, and it's what's used to convert between what you measure in your electrometer, which is in nanocoulombs, which is charge, and you apply this factor to convert to dose, so in joules per kilogram. So the unit of NDW, so this stands for, it's the calibration coefficient for dose to water. That's basically what it means. And the units would be joules per kilogram nanocoulomb, and that is the factor that you get from your primary standards laboratory when you send your reference chambers. That's what they determine from first principles, and what you try to then relate to your user or to your field chambers. And finally, your beam quality correction factor, and this corrects for the differences in your ionization chamber response between your reference conditions, say 6 megavolts, say your chamber is calibrated at 6 megavolts, but you're using it at 10. That chamber is not going to respond linearly, or it's not going to have the same response between those two different energies for the same amount of dose given. So you need to have a correction factor that accounts for this difference basically in the energy, or the energy spectrum of the beam that you're delivering. And that's another factor that's given to us by the primary standards dosimetry laboratories. And this is my final slide. So this just quickly summarizes the use cases, pros and cons for your parallel plate chambers in general, cylindrical chambers in general, and then two specific cylindrical chambers which are used here. The FC65 is a larger chamber, and the cylindrical CCO4 is a much smaller chamber. So just starting with parallel plates, they're used for electron reference dosimetry. They're used in high dose gradient regions in the direction of the beam. So doing percentage depth dose measurements, calculating surface dose or tissue phantom ratios, which are terms we're going to learn about. The pros of parallel plate chambers is that they have a small, the height of them in the direction of the beam is very small, and so you get a very high spatial resolution. That's why they're recommended for electrons, because electrons have a low penetration depth, and also in the build-up region for photons. And then they also have a thin entrance window, so that minimizes the electron perturbation compared to cylindrical chambers. And they have that guard ring, which prevents the in-scattering. It's just a much more effective design of the guard ring versus cylindrical chambers. The cons are that they have a wide sensitive region, so that leads to poor spatial resolution perpendicular to the beam. So you couldn't use it to measure a beam profile. So like if it's to measure the profile of the beam, you wouldn't use that because you're resolving like a few centimeters as you move along that profile. So you'd use a cylindrical chamber for that. Cylindrical chambers are used for photon reference dosimetry. So one pro is that they have no angular dependence in the azimuthal direction. So that's basically, you can, if you put them perpendicular to the beam, you can rotate it as much as you want. It's not going to make a change to your response. But they have a higher electron perturbation factor compared to parallel plate chambers because of that less effective guide ring. Here we use the FC65 chamber for reference dosimetry. So when you measure the output of a LINAC monthly, that's a check we do every month. We measure that it's delivering, say, we specify that it delivers 10 gray. We check that every month it's going to deliver 10 gray because that quantity tends to shift. So we use the FC65 chamber to do that. And we do that because it has very well established corrections, and it's a good balance between signal to noise ratio and resolution. So the larger your volume is of air, the greater your signal to noise ratio is going to be. So that it has a good balance between those two factors. So it's good for reference dosimetry. But the downside is that it has that larger volume. So if you're doing measurements like percentage depth dose, output factors, profiles, it's going to be less efficient or less accurate than a smaller chamber like the CCO4. Yeah, and then moving on to the CCO4, that's conversely used for the high dose gradient regions. So yeah, measuring skin dose, for example, or if you're applying patient-specific QA.
Yep, I can see it.
All good? All right. Yeah.
Can you hear it?
Say so.
Hello.
Yeah.
Awesome. Okay. So last bit. Yep. The smaller CCO4 chamber is used more in high dose gradient regions. So stereotactic treatments, patient-specific quality assurance, where you have lots of modulation of your dose, and also when you're measuring profiles. It's also extensively used during LINAC commissioning. So a lot of relative dose measurements, for example, percentage depth dose, output factors, tissue phantom ratios, and profiles, where you're not relating it to the absolute dose, but you're relating it to two dose measurements within that experiment. So that's what we mean by relative dose. So yeah, that smaller volume equals a better resolution, and it's also got well-established correction. We also send the CCO4 to primary standards dosimetry laboratories for calibration. So we have those very well-established corrections. And the downside is that you have a lower signal-to-noise ratio, but you can just slow down your measurement or run multiple measurements or just increase the number of dose you're giving to kind of account for that. And that's me. That was the first half of the presentation.